You ever notice how déjà vu feels less like a memory and more like a repeat? Not just the vague sense that something happened before, but the specific, unsettling feeling that the exact same moment, same light, same sounds, same words, already occurred in precisely this way. Most of us dismiss it. A quirk of memory, a misfiring neuron, nothing more. Except here's what's interesting. Déjà vu happens to about 70% of people, peaks in your teens and 20s, then fades. It follows patterns, statistical patterns. And when something biological follows statistical patterns that precise, it's usually telling us something about how the system works. But what if the system isn't biological? What if these moments, déjà vu, strange coincidences, those little hitches in reality, aren't bugs in our brains, but glitches in something much larger? The simulation hypothesis isn't new. Philosophers have played with the idea for centuries. Descartes wondered if an evil demon was fooling his senses, and Hindu philosophy has long described Maya, the illusion of reality. But in 2003, philosopher Nick Bostrom formalized it with actual mathematics. His simulation argument is deceptively simple. If any civilization reaches the technological capability to create conscious simulations, and if they have any interest in running those simulations, then the number of simulated realities will vastly outnumber base reality, which means statistically, you're far more likely to be living in a simulation than in the original. Bostrom calculated that if just one civilization in the universe runs ancestor simulations, detailed recreations of their evolutionary history, then simulated minds could outnumber real minds by trillions to one. And this is where it gets interesting. If we are in a simulation, we should expect to find evidence. Not dramatic proof, but subtle inconsistencies. Places where the code shows through. Let's start with quantum mechanics, because it behaves exactly how you'd expect a rendered reality to behave. At the quantum level, particles don't have definite properties until they're observed. An electron doesn't exist in a specific location. It exists in a probability cloud, a superposition of all possible locations. Only when you measure it does it collapse into one position. This is not a metaphor. This is experimentally verified physics. The double-slit experiment has been run thousands of times. Fire electrons one at a time through two slits, and they create an interference pattern like waves. But watch which slit they go through and the pattern disappears. They behave like particles. The act of observation changes the outcome. Well, it turns out, this is exactly how video game rendering works. Modern games don't render what you're not looking at. They save computational resources by only generating detail where the player's attention is focused. The universe seems to do the same thing. Why would fundamental reality care whether you're watching? Unless it's trying to conserve processing power. Then there's quantization itself. Space isn't infinitely divisible. At the Planck scale, about 1.6 times 10 to the negative 35 meters, space-time itself becomes grainy. You can't have a distance smaller than the Planck length, and you can't have a time interval shorter than the Planck time, about 5.4 times 10 to the negative 44 seconds. These aren't just measurement limits. They're fundamental. Space and time come in discrete units, like pixels, like the resolution limit of a screen. Physicists describe this as the pixelation of space-time. And while they don't usually invoke simulation theory, the parallel is hard to ignore. If you were designing a simulated universe, you'd need a base resolution, too fine, and the processing requirements become infinite, too coarse, and the inhabitants notice. The Planck scale sits right at the edge of what biological life could ever hope to detect directly. Consider the speed of light, 300 million meters per second. Not approximately, exactly. It's built into the structure of space-time as a hard limit. Nothing with mass can reach it. Nothing can exceed it. Information itself cannot propagate faster, and this speed limit is the same everywhere for all observers, regardless of their motion. Einstein worked out the mathematics, but he never explained why this particular speed. Well, it turns out every simulation needs a clock speed, a maximum rate at which information can update. In a computer, it's the processor's gigahertz rating. In the universe, it might just be the speed of light, a cosmic frame rate that keeps causality consistent and prevents the simulation from breaking. If questions like these are what keep you up at night, consider subscribing. We explore the biggest scales and smallest mysteries every week, and there's something deeply satisfying about sitting with questions that don't have easy answers. The mathematics gets weirder when you look at physical constants. The fine structure constant, alpha, is about 1 over 137. This dimensionless number governs electromagnetic interactions, and it's tuned to about 1 part in 10 billion. If it were even slightly different, atoms couldn't form. The cosmological constant, the amount of dark energy in the universe, is tuned to 1 part in 10 to the power of 120. That's a decimal point followed by 119 zeros, then a 1. These aren't just unlikely, they're absurdly, impossibly precise. Physicists call it the fine-tuning problem, and the standard explanations are either the anthropic principle, we exist in a universe that permits our existence because we couldn't exist otherwise, or the multiverse, where every possible combination of constants exists somewhere, and we happen to be in a compatible one. But there's a third option nobody wants to say out loud. These constants were chosen, set deliberately, programmed. Here's the thing, though. If we are in a simulation, it's not perfect. And maybe it's not supposed to be. Déjà vu might be the most obvious glitch, but there are others. Mandela effects, where large groups of people share identical false memories of things that never happened. The Fermi paradox, where a universe that should be teeming with intelligent life appears completely empty. Or consider this. The observable universe contains about 2 times 10 to the power of 78 atoms. That sounds like a lot, but it's a specific, countable number. A finite amount of information, a 1 followed by 78 zeros worth of particles, each with position, momentum, spin. The total information content of the observable universe has been calculated at about 10 to the power of 120 bits. Again, finite, which means you could, in theory, simulate it if you had enough processing power. And here's where Bostrom's argument completes. A post-biological civilization with access to even a fraction of the energy in their galaxy could theoretically run trillions of simulations at this scale. Which brings us back to the probability. If simulations are possible and desirable, then most minds experiencing reality are simulated minds, including, probably, yours. But let's sit with what this actually means. If reality is a simulation, does that make it less real? You still feel pain when you stub your toe. You still experience joy, love, loss, wonder. Your thoughts are still your thoughts. The sunset is still beautiful. The mathematics still works. A simulated universe with consistent rules is indistinguishable from a base universe, because consistency is what makes something real. The question isn't whether the substrate is physical or computational. The question is whether the experience is genuine. And by every measure that matters to you, it is. This might feel uncomfortable, and that's okay. We're essentially asking whether we're characters in someone else's story, whether our choices are truly ours, whether any of this matters if it's running on hardware we can't see. But consider this. Even if we are in a simulation, we're in a simulation complex enough to produce consciousness, self-awareness, curiosity, the ability to ask these questions in the first place. That's not nothing. That's actually extraordinary. The fact that a system, biological or computational, can become aware of itself, can model its own existence, can wonder about its origins, is perhaps the most profound thing in any reality, simulated or otherwise. And here's what nobody really sits with. If we're in a simulation, the beings running it are probably in a simulation too. Bostrom's logic doesn't stop at one level. If post-biological civilizations run ancestor simulations, and those simulated civilizations eventually reach the same capability, they'll run simulations too. You get infinite regression. Simulations within simulations, each layer unaware of the ones above. Which means the question, are we in a simulation, becomes less important than how many levels down are we. And functionally, it doesn't matter. Your reality is your reality, regardless of the substrate. The glitches, if they are glitches, might just be reminders, little moments where the code shows through, where the rendering gets sloppy, where the universe winks at us. Déjà vu. Quantum weirdness. Mathematical precision that feels too perfect. They're not proof, they're just interesting. And maybe that's enough. Maybe the point isn't to escape the simulation or prove we're in one. Maybe the point is to appreciate the complexity of the system we're in, to marvel at the fact that it works at all, to be curious about the architecture. Drop a comment and tell me, if you could ask the simulator one question, what would it be? We live in a universe, simulated or not, where the rules are consistent enough for us to discover them, beautiful enough to inspire us, complex enough to keep us wondering. Whether we're running on cosmic hardware or divine computation, we're here, we're conscious, and we're trying to understand. And in a strange way, that might be exactly what we were designed to do. Keep asking questions, keep looking for the glitches, keep marveling at the improbable precision of it all, because even if this is all code, it's breathtaking code, and we get to read it.